In this video, we'll take a look at the temperature dependence of Gibbs energy of reaction. Okay, so standard Gibbs energy of reaction is the Gibbs energy change when a chemical reaction occurs under standard conditions. IUPAC recommends using a standard pressure equal to 1 bar, and the Gibbs energy of reaction can be calculated from the Gibbs energies of formation of the reactants and products. In terms of the symbol, we have a delta G that represents the Gibbs energy change, a superscript circle for standard conditions, although sometimes a superscript plimsoll is used, subscript T for the temperature at which the reaction is occurring, and a subscript R to denote that this is for a reaction. Okay, general form of a chemical reaction is shown here, where we have reactants and products, and we have stoichiometric coefficients for each component and the chemical formula for each component. But this is just a very general form that we've got here that we're using to think about this problem. Stoichiometric coefficients for products are positive because they're being created through the reaction, and stoichiometric coefficients for reactants are negative because they're being consumed in the reaction. Okay, to calculate the Gibbs energy of reaction, we can use this equation here, delta GR equals the sum of each individual stoichiometric coefficient multiplied by the Gibbs energy of formation for each component. So if we look at this and put it out in stages, we've got the stoichiometric coefficient for component 1 multiplied by the Gibbs energy of formation for component 1, and we just keep adding these terms on for all of the species in the reaction. Okay, so for an example, we've got steam reforming of methane. The reactants have negative stoichiometric coefficients, so methane is -1, water -1, but they're positive for the products, so we've got the stoichiometric coefficient for carbon monoxide equals 1, and for hydrogen is 3. We can look up values for the Gibbs energy of formation for these different components, and then we can put these values into the equation and work out a delta G of reaction at 298 equals 141,863 joules per mole. In terms of temperature dependence, we have this equation here, delta G of reaction equals delta H of reaction minus T delta S of reaction. And in order to understand something about temperature dependence and actually get to the temperature dependence, we first need to look at the temperature dependence of delta H of reaction and delta S of reaction. So temperature dependence of delta H of reaction is given by the equation shown here, and we get an overall equation when we do the integration shown at the bottom of the screen here. Now we've been through this in a bit more detail in a previous video, so I'll link to that in the description below. Same thing for delta S of reaction. We can go through the steps and the stages and come up with an equation that gives us the temperature dependence for the entropy of reaction. Now that we have these two equations, we can actually put these together and think about this delta G R equals delta HR minus T2 delta S. So putting all of that together with the CP has to be in the form of CP divided by R equals A plus BT plus CT squared plus D T to the minus 2. With all of that information, we can now get the temperature dependence for the Gibbs energy change of reaction. So T2 is the temperature that we're interested in, T1 is the reference temperature where we've got values for heats of formation, enthalpies of formation, and entropies of formation. So overall, that's been a video about the temperature dependence of Gibbs energy of reaction. I hope you found that useful. Please remember to like, comment and subscribe, and thanks very much for watching.